All right, so let me walk you through this presentation here, which is about the influence of electric charges in their vicinity. We are going to be talking about a physical quantity called the electric potential, and you're going to learn how to calculate that physical quantity at a given point in space due to a configuration of point charges. For example, you have a number of charges here, and you want to calculate their influence at some specific point, or due to some continuous distribution of electric charges, so they're spread out on a surface or a line on a volume, and you want to calculate at a point P what is their influence, which is here, which is what we think of, we call it the electric potential. That's the physical quantity. And then we're going to learn how to relate the electric potential, that particular physical quantity, to these other two physical quantities, the electric potential energy and the electric field. Now, let me remind you quickly of what we mean by a charge distribution and what we mean by a point charge. A charge distribution is where you have charges that are spread out over a particular, either a straight line or a surface or a volume. So think about, for example, a certain amount of charge per unit length, lambda. We call that the linear charge density. So it's the amount of charge that sits on a unit length. Of course, if it's uniform, that means take the total charge divided by the total length. It gives you how much charge sits per unit length. It's kind of like when you're buying something by the foot. You say the price per foot, but here we're saying the charge per foot or the charge per meter, etc. Of course, we're using SI units, so we're going to be talking about lambda, the linear charge density, in terms of units of coulombs per meter. On the other hand, if the charge is spread out over a surface area, we call that a surface charge density, and you can think of it as coulomb per meter squared. So something like you're painting a room, so what's the price per square foot or something like that? Here we're talking about coulombs per squared meter. That's the surface charge density. Or you could have some volume where the charge is spread out over that whole volume, and a specific element of volume, dV, in whatever coordinate system you like. You can think about how much charge is sitting in that inside of that. We call that rho, the volume charge density, and it's how much charge is sitting inside of that infinitesimal element of volume. Now, of course, if it's uniform, then you take the total charge divided by the total volume, it gives you the charge per volume. Now, these charge distributions, of course, we know that point charges or something like electrons or protons or something like that. But even if these charge densities, if these charge distributions are small compared to the size or the scale of the analysis, so suppose I have two charge distributions that are separated by a distance that is really quite large compared to the charge distributions, then I can consider this charge as a point charge. So what we mean by a point charge is that the size where the charge is distributed, suppose I have 3 nanocoulombs, 10 nanocoulombs, you know that this is a lot of electrons or a lot of unpaired protons to make up that amount of charge. But if they're distributed over a volume or a space that is really small compared to the size of the problem or the size of the scale of the analysis, then we consider it a point charge. Now, remember from last time that we talked about the electric charge, and we mentioned a little bit the rest of the cast that comes with it. So you have that central character that is playing the role of this, the new protagonist in the story. And then there are all these new characters that we're going to have to think about in relation to this thing. So there are going to be some characters that are just about the influence of that charge. It's only about what it's doing in its vicinity. And there are going to be some characters that are about the interaction between this charge and some other charges. We call this the potential energy or the force. We've talked about electric potential energy. We've talked about gravitational potential energy, elastic potential energy in physics 1. This is an electric potential energy, and we'll see how that comes into play. And then we're also going to learn about the relationships between them. So we're going to think about all of the map of the relationships between how to think about, okay, if you have one of these physical quantities, how do you acquire the other ones, and so on. Now, in this particular story, we're focusing on this electric potential. And of course, I can start from the charge and I can play this game. For example, most textbooks you'll find they go straight to the force because you have familiarity with the concept of force. So they start there. And then they define the electric field. And then based on that, they define the electric potential. I am going to start with you with just the electric potential directly. We're going to start here, and then we're going to see its relationship to the energy and to the field, and then later we'll see how that generates the force. Remember that these concepts are not, they're only new in the context of this particular kind of story. It's about the electric story. But we've learned some of these things in the gravitational story. We've learned about the gravitational force. We've learned about the gravitational field, even though we didn't call it that. We learned about the gravitational potential energy. So it's quite analogous to the story that we're studying now, and we're going to rely on this analogy a lot when we're solving this. Conceptually, you can think of the electric potential as some kind of glow around the electric charges. It's quote unquote glow, like sort of this fictitious thing that is around the charge. Of course, we can't see it, it's not there, but it's fictitious. In this particular simulation, it's representing by these curves, and you can see how they get denser as you get to the charge. I think I can think about just looking at them from a different perspective. So the charge has this influence around it over all space. We just sometimes, to visualize it, we take a 2D slice so that we can see what it looks like, because it's difficult to see in 3 dimensions. You can also think about any kind of distribution of charge. For example, if I have a charge line, then I can think about what the influence around that line looks like as I move. And then I can think about it in the Z space as well. So you can see what that electric potential of that line looks like. And you can play with these, and you can look at all the different situations where we're going to study later in the course. We're going to try to find out the electric potential due to all of these different charge configurations. Now, if I'm thinking just about, in general, about a charge, about a point charge, for example, then I'm going to tell you 3 pieces of information that are really critical to defining this electric potential. The one is that the electric potential due to that point charge is proportional to the charge. That means doubling the charge doubles the electric potential at some point. So suppose I fix the point, and then I take that charge and I double it, then the potential at that particular point would double. So the potential at every point in space would double if I double the charge. That's what I mean by the electric potential is proportional to the charge of that point charge. The electric potential also turns out to be inversely proportional to the distance from that charge. So suppose I have a charge Q that is sitting here, and this is some kind of local coordinate system where I'm sitting Q right at the origin here. And then I'm defining a point P that is some kind of distance r away from that point charge in some direction. And you'll notice that the story here doesn't talk about the direction at all. It just says inversely proportional to the distance. And remember that the distance is a scalar quantity, no direction information here. So that means that all of the points that are distance r away from that charge are going to have the same potential. And if I double the r, I halve the potential. That's what it means to be inversely proportional. If I double the distance away from the charge, that means I halve the potential. The potential at a distance 2r is half the potential at a distance r. Now it keeps getting smaller and smaller and smaller as r gets bigger and bigger and bigger. It's also the material between the charge and that point really matters. So the electric potential will be dependent on that material in the region separating the charge and its location. Now, in general, we can figure out exactly how to calculate the electric potential if we know what the material is. But in this course, if the material is not mentioned, we're just going to assume that it's in vacuum. So putting all this information together, this is the expression that we find for the electric potential due to a point charge. It's proportional to the charge, so it has some kind of constant of proportionality, K, which is really material dependent. And then because it's proportional to the charge, that means the charge is in the numerator here, because 2q would give me 2v. And then it's inversely proportional to the distance, so 1 over the distance is multiplied to give me the potential. So the potential then due to a point charge would be kq over r. This is only due to a point charge. If I want to find the potential due to configuration of charges or some other kind of distribution of charges, I would have to rely on some other way of thinking about it to figure out what the potential is from that distribution of charges. But if I just have a single point charge, and again, the definition of the point charge is that the size of the charge, meaning its spatial extension, is small compared to this distance r. So this the size of this Q, not the magnitude of it, not how big the net charge is, but how where is it distributed. So if it's distributed in a very small volume compared to this distance r, then we call it a point charge. And this is how you calculate the potential due to that point charge. If now it's only dependent on the distance r, so I don't have to really think about this three-dimensional picture for now. I'm just going to think about this distance r and the dependence of the potential on the distance r, just to illuminate this point again. So this is here just a simple plotting of the kq over r. I'm taking k to be 1 in this case just to illustrate the shape of the thing. I don't care about the numbers much, but I just care about the shape for now. And you can see that as I increase the charge, you can see how the potential, so in this particular case, I'm putting the charge right at the r equals 0, right? Because r is always the distance away from the charge. So when r is equal to 0, that's where the charge is. And you can see that the potential is really high. You know, it's not really defined at r equals 0, right? Because if I divide by 0 here, I get an infinite potential, quote unquote. So I'd rather just say that it's not properly defined. Like, what does it mean to talk about the potential right at the location of the charge? So I ignore that. And what I talk about is, what if it's a distance r away from it? Let's say at this red line here, you can see that as I increase the charge, then the potential increases. If I go the charge from 4 to 8, then I'm doubling the charge, then I would double the potential. At the same time, if I look further and further away from the charge, the potential gets smaller and smaller and smaller, asymptotically reaching 0 when the distance goes to infinity by definition. Now, obviously, there is no such thing as an infinite distance. So we say as the distance goes towards infinity, as I get to a larger, much larger and larger and larger distance, the potential asymptotically goes smaller and smaller and smaller, asymptotically going to 0. Now, here's an interesting thing that happens too, which is what happens if the charge becomes negative? If I put the negative charge, then this potential is going to be negative because the charge will be negative, everything else is positive, so the potential will be negative for a negative charge. Now, the potential is a scalar quantity. So the positive and the negative here are not indicating any kind of direction information. Positive and negative are more indicating something about more or less. Is it a higher potential or a lower potential? So negative 5 volts is lower than negative 4 volts, right? Keep going smaller and smaller, even though so for example, if I get closer and closer to the charge, the potential starts going down and down and down and down. So it gets more negative. So that means lower potential. And again, asymptotically reaching 0 as R gets very big. So to summarize, the electric potential due to a point